In this session, we are going to study the magnet. Magnetic phenomena was first observed 2500 years ago in western Turkey. Still now, we experience many magnetic phenomena using the permanent magnet. Sometimes we use a compass to find the direction of north. Magnetic force has an attractive force and a repulsive force, as you might know. If you consider the two different magnetic poles, N and S, is attractive force acting between the N and S. If you consider the N and N or S and S same pole, then repulsive force is acting between the two magnets. Actually, this is a very big difference between the charge and magnet. In the case of the magnet, there is no monopole. Poles always appear in pairs. So this is a permanent magnet, N and S. If you cut this magnet at half, maybe you might think that we expect one of the magnet becomes S. The other one is N. But this is not true. Even if you cut in half of the original magnet, next magnet always has an N and S. Always poles appears in pairs, N and S. This is a really big difference between the magnet and the charge. Magnetic field of Earth. So Earth itself is a magnet. Is written by the William Gilbert, 1600. So because of the Earth has behaved like a bar magnet, we can use a compass to find the direction of north. So this is a compass, and then the N is directed always toward the north. So this means north doesn't have a N pole. North has a S pole. Because the north has a S pole, N pole of the compass experience the attractive force toward the north pole. To express the directions, we use the two angles of the D declinations and the inclinations. And to express the magnitude of the magnetic field, we use a total intensity. Really important discovery done by the Elsted in 1820s. If you consider the wires, then flowing the current on these wires, so current is flowing on the wires. Then this flowing current produces the magnetic field. And the magnetic field is directed in this direction. So to find out this direction, you can use a right hand rules. So your thumb is pointed to these directions, and the fingers. Try to roll your fingers. The direction of the fingers corresponds to the direction of the magnetic field. Okay, magnetic field and the current is closely related. Was discovered by the Elsted 1820s. Actually, if you consider the atoms, in the atoms, nucleus is located at the centers. Nucleus has a positive charge. The negative charge of the electron is rotating around the nucleus. So this is the direction of the motion of the electrons. Then we could consider the current. Direction of the current is the opposite direction with respect to the direction of the electrons. So this is the direction of the current. If you consider this current is flowing in atoms, then we could consider that these atoms produce the magnetic field of B. Current due to the circular motion of an electron in atoms generates the magnetic field. Magnetic field is also induced by the electron spins. So from these simple discussions, atoms produce the magnetic field by itself. To describe the magnetic field, we use a B, with a vector. Direction is defined as the directions in which the north pole of the compass needle points. So this is the direction of the B. The length of the arrows correspond to the magnitude of the magnetic field. The unit of the magnetic field is expressed using Tesla. T, capital T, is we call the Tesla, after the famous American physicist Tesla. The magnetic flux can be defined in the very similar with electric flux. So if you consider magnetic flux through these areas, you can consider the scalar product of B dot A. This is scalar product. Magnetic flux is defined with a scalar product. So B dot A is a BA cosine theta. Theta is the angles. The unit of the magnetic flux is a Tesla. This is the unit of the magnetic fields times the area. Unit of the area is square meters. We introduce a new unit. Weber is a unit of the magnetic flux. Then finally, I'd like to introduce second fundamental equation for the electromagnetism. Is a Gauss's law for magnetism. Electric field lines begins and end at charges. There is no magnetic monopole. The magnetic field line forms closed loops and never have the end point. So always in the magnet, N and S. So this starting, and then for the S is coming. In the case of the magnet, always poles appear in pairs like N and S. If you consider any closed surface, so in this case the blue figures, always outward flux and the inward flux should be cancelled out. So if you consider the surface integral of the magnetic field, it becomes 0. So from here to the here, you can use the Gauss's theorems using the del operators. The del dot B equals 0. So you can take any size of the closed surface. It's independent of the size of the closed surface. So it becomes del operator dot B equals 0. This is a differential form of the fundamental equations of the Gauss's law of the magnetism. So this is the expressions of the Gauss's law for the magnetism in an integral form. Okay, I introduced the magnet in this section, and also I explained the second fundamental equations for the electromagnetism, Gauss's law for magnetism. Okay, this is the end of this session.